Michael Collyer. If anyone has done landmark analysis, might know that he's the co-author of the geomorph package, which is really the package for landmark analysis, and also the author of the RTP.
Some people say R2P2.
Okay, that's easier, yeah. Which also is an R package for multivariate statistics of extreme high dimensional data, like the stuff we're talking about now. So really important in that field between biology and analysis of shape. And yeah, we've known each other well, mostly by email, but then we did a workshop together. I did a workshop with Geomorph in Chile some years ago. So really happy now.
Yeah, it was nice to no longer be pen pals.
Yeah. So welcome, Mike.
Thanks, Chrissy. It's great to be here, but I'm really excited about this talk because this is the first time I've done something like this. I get to talk about one of the more fascinating and exciting and intense areas of research I do that usually goes unnoticed, just because it's really not primary scientific research. It's making your research better. It's almost service related. But this is the kind of stuff that just gets me out of bed and gets me excited. Call it my obsession if you want. Basically, the computational side of being able to perform landmark-based geometric morphometric analysis. And I want to start by putting this picture up of some participants in a couple different workshops. I was in two of these. The first one here in Rome, I think I might be that speck back there. And the second one here in Pescia, Italy, that's me right there in 2010. The reason I want to start with this is 2002. It was 20 years ago that I was at my very first geometric morphometrics workshop. That time I was a student just trying to understand this stuff. I couldn't understand all these mathematical equations. I didn't know what was going on. I just trying to keep my head above water because I had a PhD project that needed data analysis and I wanted to be on top of it. 8 years later, when I was in Rome, much different situation. Now I was a faculty member at a university. I was running my own research lab, and I found myself starting to think about how we analyze data with geometric morphometric shape data, and started to kind of push some boundaries at that point. So when I think back to that 20-year ago workshop, what were we learning at that time? I got these figures from a special issue that was produced mostly on research that was presented at that workshop. I just want to show you some of these simple landmark configurations. There were people who were working with 3D morphological structures, but they were using multiple planes of 2D images. And this was published 2 years after that workshop. At that time, we never heard about semi-landmarks. We would spend time learning about John Krusty's analysis, EDMA, Bookstein coordinates, which was better, which was appropriate. And I highlighted something here. I don't even know if most of you even know what this is, but we used to learn about relative warp analysis where we could weight partial warps, and we would discuss which was appropriate, whether that there should be any kind of weighting. This was the field at that time. And then in 2004, when this was published, you see this nice little 3D image here, which was stolen from Philip Mitterrocker's master's thesis, kind of getting into 3D morphometric analysis. And you can't probably read it here, but the future of the revolution in morphometrics, use of three-dimensional data. It was just a concept at that point mostly. However, maybe if you go to a workshop, say 10 years ago, it starts to look different, right? We start to see a lot more high-dimensional 3D data. We start to see better imaging techniques for visualizing shape change in 3 dimensions. And then we also start to see, here's my contribution here, things like trajectory analysis, the ability to use these complex data to answer interesting hypotheses. Anjali was part of this volume as well. You guys were kind of probing the use and misuse of phylogenetic principal component analysis. So we were spending a lot more time bringing evolutionary biology and phylogenetic comparative methods into the geometric morphometric workshop toolkit and worrying less about how we get our data, but what we do with them. And I would imagine that if you go to a workshop now and it's your first experience, there's a lot less about how we do geometric morphometrics, except from a historical perspective. High dimensional data is no longer considered an issue. We don't worry about how we analyze data. I can remember in that first workshop trying to find the smallest number of landmarks I could to have statistical power to do my analysis. Now we go the opposite way, right? We use more information. So we wrestle less with the appropriateness of the data, but more with the appropriateness of the analyses we use with the data. And we focus on things like modularity, integration, combinations of multiple shapes, and phylogenetic comparative methods, things like phylogenetic signal, how to perform phylogenetic generalized least squares. These things were never part of the workshop experience 20 years ago, but they're prominent parts today. But what most workshops probably don't do, and I'm going to do today, and I hope it doesn't sound like a complaint, is talk about what a burden this is if you're the one making the software, because the last thing you want is people to hate your software because it takes forever to run. And when we have large data sets now, large 3D data sets, doing generalized least squares estimation, maybe we have landmarks on surfaces that can slide all over the place, so we got to mess around with that. These are computational burdens that make people like me, a programmer, these are really challenging things to overcome. But in overcoming those challenges, we create new opportunities for methodological advances. And what I'm going to point out today is we might also discover some tendencies that maybe we should avoid. And I'll get into that more at the end of the talk. So what I want to do now is get a little more technical. And if you don't like the technical parts of this, I'm trying to put translations, simple word translations at the bottoms in a different color text. Basically, this is what I want to talk about. You can just go to and read that like a subtitle if you prefer. Hopefully I capture everybody's interest in spite of your prowess with linear algebra. But describing a linear model starts like this. We have a data set, a matrix Y. We have maybe n observations and p variables, and if we have high dimensional data, p is really large, right? We have X, which is our model design matrix. It also has n observations and k model parameters for describing how a phenotype or any other type of data might change based on the parameters in that matrix. And we have omega, which is a matrix that describes the non-independence among our observations, if there is any. In other words, if we can't assume that observations are independent, how do we expect them to covary? So it's also a parameterized matrix. And then we estimate coefficients from our linear model with this pretty general equation you can find in any statistics text. I won't get into all the details, but I'll gladly talk about it outside of this talk if you want to know why it's done that way. We can calculate those coefficients, which explain how something like morphology will change based on parameters in X, but we also might want to say, what are our expectations from that model? So what we can do is multiply those coefficients times some matrix X. And I put a tilde over this because it might be our original X linear model design, or it might be a new one. If it's our original, we can find fitted values from our linear model. If it's a new one, we're finding predicted values based on the training we used our data for those coefficients. So I got a little algebra here where I expand this out, and all this gobbledygook here we'll just call H, which is a hat matrix. Why do we call it a hat matrix? Because we're going to find Y hat, right? And if you look at just this last part of the equation, you can recognize that what a model does is it transforms the data in some predictable way. That's all it does, right? We can ask if that's a good transformation or a bad transformation through various statistical techniques, but that's from now on, I'm going to just keep putting this up here just to show that what we're doing is creating some model for how our data should change. For example, if you've done a generalized Procrustes analysis as a method of shape analysis, we calculate a model. And we have an equation that looks like this, where Z is a matrix of Procrustes residuals. I'm going to go over to the right sides here. It might be, those residuals might be scaled. So S is 1 if we're talking about Boas coordinates. or its centroid size if we're standardizing the size of our specimens. There's that H matrix, which finds the shape mean, and this identity matrix, subtracting it there, that's translation. That means we take our landmark coordinates and put them all in the same spot, and R here is a rotation matrix. So H here, again, a hat matrix, solved the same way. In our model design, X is just a vector of ones. Omega is just an identity matrix, meaning the landmarks are independent of each other. Now, they're really not, but in terms of rotating, we assume that they're independent. So basically, we use a model to update our landmark configurations in GPA, right? And some of you have maybe done generalized Procrustes analysis that involves sliding semi-landmarks. Well, that's also a hat matrix. We replace X with this matrix U, which finds the tangents of sliding semi-landmarks, or our 0 for our fixed landmarks. And this L sub K matrix here is a Kronecker product of the bending energy matrix, a very large matrix if you have lots of landmarks, especially in 3 dimensions. This is something that also has to be inverted, and I'm going to talk about that later as a computational challenge. But what we do is we create this model and we update a vectorized form of our landmark data, Y, and once we change it, we add it to the original, which gives us an updated version. Do this over many iterations, and Y prime here is the result. These are our transformed landmarks. Pretty simple. Maybe once we have our data, we want to analyze them. So now Y, instead of being a landmark configuration, is a series of landmark configurations that have been put through the ringer with generalized Procrustes analysis. Maybe we have an interesting model, which we'll call the full model here, that has lots of parameters. We have a reduced model that takes some of those parameters out. Are those parameters important? Well, let's compare the 2 models. How do we do that? We simply do a matrix square, Y hat transpose Y here, to find the squared values for our fit with the full model. We do it for the reduced model. We subtract one from the other, and then we get the trace of that matrix, which gives us sums of squares. Here's another way of looking at it. The model matrices themselves, since they're symmetric and of the same size, we can just find the difference in the models, and again, transform the data by the difference in the models instead of single transformations. Algebra is a beautiful thing sometimes. So these are 3 examples that you might not recognize, that all we're doing is just making models, updating them, comparing them, whatever. That's multivariate statistics, in my opinion. So this is the beginning of an analysis of variance. So the take-home point here is that everything we do, we create a model, we transform the data by that model for some specific purpose. Now that I've said that, this is my linear algebra teaching of this subject. When you go to use your computer to do a data analysis, I don't do that with the programming. I don't create these hat matrices necessarily. And the reason for it is that the hat matrix is typically symmetric and can be large, often might contain lots of zeros. And when we're talking about computations, multiplying 0 times something plus 0 times something plus 0 times something is a waste of time. Also, our data can be really large as well. And when you're multiplying one large matrix times another, that's something that can take a long time. So, you know, what I end up doing is trying to find solutions that are quicker. And just to help make this a point, I don't know if you can see my code up there, but I'm going to have a series of slides here that have R scripts. What I'm doing is I'm making a list of research subjects, each with 3 observations, 5 research subjects, 3 observations each, and I want to make a model that estimates subject means. So I use the code here to make a model matrix X. Then I find the hat matrix, and what I'm doing here is saying, give me an image of that hat matrix. And what you might notice is there's some information along the diagonal there, but most of that matrix is empty. Where you see nothing, those are zeros in the matrix. Where you see a shaded box, that means there's some value there. So there's a lot of missing information in this matrix, right? And I'm going to say this is complex, yet it's a sparse matrix. Why is it complex? Because I'm estimating subject means. I could just estimate an overall mean with using a model that has nothing more than a vector of ones. And when I create a hat matrix, now we have a dense matrix that's really simple. Every value in this matrix is 1 divided by the number of observations, 15. 1 divided by 15 over and over again. So this is kind of a paradox because we create a complex hat matrix from something simple and a simple hat matrix from something complex. You know, just to remind you, these are what the model matrices look like. A vector of ones in one case, and then this matrix here has lots of zeros or ones to indicate parameter-wise whether we're talking about subject 1, subject 2, subject 3, and so on. So if we wanted to do something like compare those models, in other words, do we want to ask if subject means are different from each other? What we would do is get our 2 different hat matrices, multiply them times our data, and then what we could do is square those things and take the trace, and we get 2 values here, 8.33 for our full matrix and 1.61 for our reduced matrix. Do you see why I'm calling this full and this reduced? This matrix exists in this one, right? And we reduced it by removing parameters. So I compare those things by just taking the difference in sum of those squares, and I get 6.7 here. If I divide that by the total variation in my data, I can say research subject explains 18.6% of my variation. And then I might perform other steps in ANOVA to determine whether I want to reject the null hypothesis that that simple model is useful and go on with the more complex model. That's analysis of variance. So it's easy to understand, I hope, if I explain it that way, but that's not what we do when we calculate sums of squares most likely. What I did in that previous step was I found this value, the trace of the cross product of fitted values, right? And I did it for 2 models. Here are 4 ways we can do the exact same thing. This is what I did in that example, but you know what we could do? We can multiply h times y just 1 time and square all the values and then sum them. That will give us the same value. We could also perform a QR decomposition on our design matrix, which finds a rectangular matrix Q and a triangular matrix R, such that the hat matrix equals Q times Q transpose. And instead of using H, we could use the transpose of Q. Do that multiplication, square the values, and sum them. We can even do this, and this is really cool. We can multiply Y times its transpose and create an n by n matrix, just like the hat matrix. And instead of doing vector products, we can just multiply element by element each value of the matrix. That's what this means here, an element-wise multiplication. And then we can sum those values. And if you don't believe that this does the same thing, there you go. Right? I just did it 4 different ways and got the same answer. 4 ways to basically skin a cat. But here's the problem. And you probably can't read this very well, but what I decided to do is say, let's do those 4 multiplications. Let's do them 100 times and create some violin plots to see if one's more efficient than another. Here's the original, which uses the hat matrix. Here's using the Q matrix. You can see where that's a benefit, right? Save some computation time. And then the others are somewhere in between. But if you're reading this closely, you might see here on the label, that's microseconds. Oh boy, I sure would hate to wait 40 microseconds for that analysis. That's not a big deal, right? It's kind of a splitting hairs thing. Well, let me tell you why this matters. Back in 2015, some colleagues and I published this paper where we introduced randomization of residuals and a permutation procedure. Happy to talk to you about all the details of this later, but this is a non-parametric way to use a resampling procedure to create distributions of statistics for ANOVA tables, especially when you have high dimensional data. Remember I said in that original workshop, I was doing this with configurations. I was working on desert fish. That top one there kind of looks like a fish, doesn't it? But somewhere around 2010, we had sliding landmarks, and that one looked a lot better as a fish. The problem is this, here I would sometimes have more landmarks than I would have research subjects, which rendered parametric multivariate statistics useless. But if I did something like a principal component, here's the 10 landmark version, here's the 56 landmark version. In which case can you discern males and females and two populations better? Notice that the clouds here are a little, the convex hulls are a little more separated. We have a better ability with more morphological information to discern among these research groups, right? So why the hell do we not have statistical power? But by employing these methods we introduce, what's being shown here in these columns, Z, these are standardized effect sizes. You will notice that they're greater if we use 56 landmarks, and we have the ability to reject a interaction in this ANOVA table, reject the hypothesis that we couldn't do with 10 landmarks, learning that sexual dimorphism is different in these two populations. So yeah, that's great. And you know, why does my previous slide, why do those microseconds matter? Because when I'm doing model comparisons here, I got 3 terms plus the whole model itself, means 4 pairwise comparisons between the predictions of models. And I did this for 10,000 permutations. That's 80,000 times I have to calculate H times Y. Microseconds matter, right? Milliseconds matter even more. You know, you don't want to have to set up your analysis and go have lunch and come back and find out that you screwed something up, right? So it does matter. So computational burdens, how do we overcome them? Well, I showed you one, which is QR decomposition. That's a good one. There's also something called sparse matrix algebra, which instead of creating these large matrices that have lots of zeros recorded, only records the non-zero values and where they would occur in the matrix. It's a different kind of data architecture. Maybe we can use that too, right? And avoid calculating 0 times something many times. So let's just see, maybe a sparse matrix algebra works better. So I'm going to use a more complicated example here. Let's imagine 400 butterflies, each with a left wing and a right wing that we've digitized, and we want to know basically if there's asymmetry in their wing shapes. So I have one factor here, subject, where it's 400 repeated each twice. And I got this other factor side, which is either left or right 400 times. I'm going to make this model matrix X, which is going to estimate the means for the left and right side. Then I'm going to find Q and I'm going to find H. And if we do that, notice that the object size of H here is about 5.1 megabytes. The object size of a sparse alternative of that same matrix is only 3.84 megabytes, meaning it takes a lot less memory to store the same data. So if we do something like these violin plots again, this time it's milliseconds, so it's really important, right? You will notice that the sparse alternative version of this means faster computation times, where you have less memory burden. That's good, but I got 2 things there. Now let's add the Q version. So now here, these are the same as that previous plot, but using the Q matrix is a lot faster than that, right? So given these 2 alternatives, whether you use QR decomposition or matrix algebra, it's QR decomposition, right? Right? Yeah, right? Not so fast. Because I had a simple model design that just said, give me a left mean, give me a right mean. Now let's find one that says, give me all the subject means, and also give the deviations of left and right wings from those means, a much more complex linear model. Now notice that the Q matrix is 5.1 gigabytes, and the H matrix, the hat matrix, is 3.84. And when we do a time-by-time comparison here, there's the QR decomposition, there's the sparse matrix algebra. 2 different examples, reverse of outcomes, right? So what's a programmer like me supposed to do? You know, what do I do with this information? So what we've learned so far is there are multiple ways to skin a cat, right? For all you anatomists here, there are multiple ways to skin a cat, right? So knowing what kind of cat you have might be informative for the best way to skin it. But if I'm making the software you're going to use, I don't know what kind of cat you're skinning. Maybe different people are going to have different experiences. So this is a challenge that I'm going to return to a little bit later, but what I want to do now is amp up our examples. I love my job. I no longer collect morphological data. I just make it. So I made a hypothetical, this is a template where I could make a dome and decide which one of these are sliding semi-landmarks in red and which one are fixed in black. And I could, whenever I'm doing something like trying to improve the computations of my software, I use something like this to do a bunch of tests. So I can simulate data on this template and do a bunch of analyses. And I would like to come to something that changed 20 years ago to 10 years ago in these workshops, the use of semi-sliding landmarks. Has anyone ever used them? Yeah, I know Ancheli has. She uses them a lot. I pretty much think this is the only work, that theoretical work that's been done on this. This was Goons et al. Back in 2005. And basically, here's the algorithm. You get tangents for each semi-sliding landmark. You relax them against the first specimen, then you get the average, then you start getting new tangents and you relax them against the average. The relaxation means to slide the semi-landmarks on tangent planes to minimize bending energy. And then you keep repeating that until convergence. Now, I've looked all over this paper and I don't know what convergence means. Okay, they don't define what convergence means. And when I learned about GPA the first time, you know, it was this function where the variation among landmarks decreased until it stopped decreasing, and then you said good. So I think that's what convergence means, but it wasn't discussed. And has anyone ever asked what their program's doing when, boom, it gives you a result? So I think the impression was that there was some monotonically decreasing function. And I'll come back to that a little bit later. But semi-sliding landmarks are a huge computational burden. There's that equation again that I talked about. And I'm going to talk a little bit more about each of the parts. That U matrix is a PK by Q matrix, where Q is either equal to P if you got sliders on curves, or equal to 2 times P if you have a surface, or 3 times P, the number of points, the number of landmark points, which might be thousands, if you have both. There's that Kronecker product of the bending energy matrix again. And as you can see here, that matrix needs to be inverted. I don't know if you ever tried to invert large matrices. Not a fun thing to do. It takes time, lots of computation involved. If I show you this template again, I've reduced it here so I can get my words. This LK sub K matrix is 3,267 by 3,267 elements, and it needs to be inverted. And that U matrix has lots of zeros, so we've got a lot of computational inefficiency there. And this needs to be done on every landmark configuration for every specimen in your study in every iteration. Not just once, but thousands of times. Well, I'm going to give you the solution, but I'm not going to tell you about the years of painstaking research that went into it. And it's something I call linear model checkers. Now, first of all, we're going to let Z here be a PK times 1 vector, a vectorized form of our matrix of landmarks. What linear model checkers does, remember that picture I showed you of the model matrix, or the hat matrix image? Didn't it kind of look like a checkerboard? I call it linear model checkers because I want to work where the information is, not where the information isn't. So it's an algorithm that finds the parts of the matrix and works there specifically. And here's how we can do this for sliding semi-landmarks. We can get A, which is a product of U, the transpose of U times that big bending energy matrix inverse. Then we multiply that times Z to get B. We multiply it times U to get C. And then here's the important part, number 4, throw A away because it's taking up computer memory I don't need anymore. And then I multiply U times C inverse times B, and it produces the same result as H times Z. It looks stupid, but let me kind of show you what this does. By parsing this out and doing the calculations, we get something like this. Now, I simulated data that was wide. By wide, I mean lots of variables in my data matrix. 524 fixed landmarks, 500 semi-landmarks, and did this for 50 specimens. I think we can all agree that's a very large data set. I also did long data, which uses only 20 fixed landmarks and only 16 semi-landmarks, but for 5,000 specimens. Another big data set, but they're big in different ways. If you use geomorph last year, it would take over an hour to do the wide. It would take about 20 minutes to do the long computation. With linear models checkers, I got both of those down to 2 to 2.5 minutes. That's how profound that difference is. Now, the other thing is using linear model checkers means using less memory, which means you can parallelize a lot of these processes with parallel processing, 44 seconds and 113 seconds. Now, geomorph is not the only program that does this, so I brought Morpho in for comparison. Very good program. The Slider 3D, 76 seconds, not too shabby. They also use parallelization. They also use sparse matrix algebra. But for long data, 53 minutes. So Morpho has an optimization that was great for wide data. We got an optimization now that works both for wide and long data. But I'm not done. I looked at this for so long and it bothered me. No matter what, if I use sparse matrix algebra, I still can't stop that from being a very large matrix product. And it made me insane because there's so many zeros in that U matrix. So I can ignore those in my computations. But this is what bothers me. Look at this picture. These red landmarks, we want to wiggle. And all those black ones need to stay fixed. But a bending energy matrix uses all those landmarks. Do we need those black landmarks to infer what we're going to do with the red ones? Do we need all of them? Here's an idea. Let's use half of them. And if we do that, we go from 524 fixed landmarks down to 200 and something. We end up with 757 points instead of 1,024. In other words, there's 641,601 fewer elements to involve in a inverse. So what if we excise that? What does that do to our computation time? So this is what we're going to do. We're going to use only a portion of the fixed landmarks, say 50%. Now we can more easily invert that bending energy matrix. We can use parallel processing more efficiently. We can run more iterations in a short time. And now I've got these analyses that took over an hour or over 20 minutes a year ago, running in 34 seconds or 28 seconds on the same computer. That's huge. Just think of what this means. And I'll explain more what it means in a moment. And if you're wondering, can we rely on these results though? You're throwing out information, right? Just to perform an analysis faster. These are the scallop data that you can find in geomorph. Here I'm using a full thin plate spine to estimate bending energy. Here I'm using 50% of the landmarks, the fixed landmarks. We call this approximate thin plate spline. If you can look at those and see differences, great. Or here, let's do a principal component analysis on these 5 scallops in each case. They look pretty much the same, right? So throwing away those fixed landmarks to increase computational proficiency didn't hurt any. This is cool. Now, I've also done this for analysis of variance. I don't expect you to read all that. That's just a screenshot. But let me say that this is what I've been able to do there. I've been able to sense the environment, find out whether I should be using Q or H or a sparse estimate of Q or H in each case for every model term in analysis of variance, and then map those out across all iterations. Here's the simple way to say it. Yes, there are multiple ways to skin a cat, but with linear model checkers, we can skin multiple diverse cats multiple ways at the exact same time. So when we do something like this, here before we had linear model checkers in Nova for those same example data, 10 seconds or 696 seconds, in other words, 11 minutes. And you can see now that we can use linear model checkers and parallelize that. It's more than a 10-fold reduction in computation time. By the way, I left out a lot of details here, but the principle, this is a gross generalization. You know, there's other things we can do, but the principle is there. So I just want to wrap up here with kind of a conclusion, but talk about what this means. Now, I'm trying to figure out a way that your geomorph user experience is better. But in the process of doing this, I start making some discoveries. So I'll start with the conclusion first. The nice thing about linear model checkers is it's dynamic. These algorithms can be improved. They can get better when we start developing faster processors that with more threading, they can be improved. But what this should mean is with greater iterative power, you can start thinking about much more complex anatomical configurations, right? And there shouldn't be as much limitation. So that's great. It's not just better now, it's better for the future as well. But there's this new, or I would say forgotten frontier I started thinking a lot about. It's semi-landmarks and surface morphology. Since 2005, there have been two ways to do this. We can use bending energy, which infers or assumes a spatial process, or minimize Procrustes distance among sliding landmarks, which means spatial independence. We can do one of those two things. I'm pretty sure using approximate thin plate spline for bending energy might mean that we can find better solutions. And here's something I bet you've never done. I did GPA here from 3 to 100 iterations. In gray, we're using minimized Procrustes distance. In black, that's the full TPS. You can see the black line going through here, kind of masked by other things. And then I did different approximations of thin plate spine using, what is it here, 30, 50, or 70% of the fixed landmarks. This gray is what we expect with GPA, but we can see that this is a much more stochastic process that might not find convergence. And convergence might be found with different interpretations of what that spatial process should be. So it actually worked out best here in blue with using 50% of the fixed landmarks, but it also worked out well using only 30% because we weren't having so many fixed landmarks constraining what we were doing with the semi-landmarks. It's kind of sad that this area of research kind of stopped in 2005. I think there's much more fertile ground. And let me also make this recommendation. When you do generalized Procrustes analysis and you get results, those aren't solid results. You should really think of this more as an exploratory analysis. And if you get results, whatever they are, you're using my judgment based on program defaults that I put into GPA Gen and Geomorph. And I just stop it at 10 unless you ask for more. Doing things like this kind of exploratory analysis with your data, maybe not a bad thing, but I really think there's also a need to think about the spatial processes that should be used when we're talking about covariance of semi-landmarks. So that's a caveat number one. GPA should be more explanatory. Caveat number two, there are many unexplored details with semi-sliding landmarks. Remember I mentioned these tangents? What are those parameters in that U matrix? Well, it's simple. We just get for each landmark, we get a principal component plane to the surface, like the tangent space that we could project into, right? How do we describe that? Well, I don't know. Let's take like the 5 nearest neighbors. That sounds good. Well, what if you have really dense landmarks versus really sparse landmarks? Those are different solutions. No one's ever explored this. We just use the suggestion that Gunz et al. Said. So if you have scanning software that creates a field of rather dense uniform landmarks, and you're using lots of high density landmarks, do we even need to use bending energy? Let me tell you this. This is good. I can show you other examples where bending energy doesn't stop, or where the criterion doesn't stop increasing because you slid landmarks off of curves or surfaces. It's possible. Convergence is not guaranteed, and it probably never happens. It probably just arrests the analysis. So should other processes be considered? It was really exciting to see some of that, the talk this morning about stochastic processes, because I think there's a solution for semi-sliding landmarks to not use linear transformations based on large sets, more localized stochastic processes. Probably a way to go. And I didn't even get to talk about something I would like to talk about, which is this opens up the opportunities to not just use a landmark configuration, but multiple landmark configurations for organisms that might be integrated in some way. So we can just start describing complex phenotypes, complex morphologies, not shapes, but combinations of shapes. Well, this is something that we kind of got into 2 years ago. How do we combine multiple landmark configurations? Not as easy as you think. It means weighting configurations that you are combining by some a priori knowledge of how they should be weighted. We provided a framework for doing that, but man, guidelines for how you should make those weights, those really need to be developed. So just an appreciation that with greater power, we have these newer opportunities, but that just also means more unexplored area that needs to be researched. Well, that's as far as I'm running this today. Normally I have a long list of acknowledgements, but I really have to say this is all my tinkering, so I don't really have a lot of people to acknowledge, but I will acknowledge my research lifelong partner, Dean Adams, because I'm always bouncing this stuff off of him. So he's been, and as you know, he's the creator of Geomorph. So, you know, a lot, great synergy. And I guess I also have to thank the NSF for allowing me to do crazy shit like this and call it a job. Any questions? Yeah. Mm. So this is going to be very data dependent. I use the scallop example. I've seen other examples where the number of fixed landmarks are few. So as soon as you start reducing them, the results can get wacky pretty fast. One thing I'll also say, even though these look like better solutions, it's a quantitative thing. What Q is here is a measure of the landmark variation. It's a quotient that can decrease to a certain number and you would stop it. The solution that might cause that, like in the case with the blue line here, doesn't mean that you have anything that resembles morphologically what you started with. So the easiest answer is I don't know, because this is so unexplored. I have found with data sets that have a lot of fixed landmarks, you get, it works a little better. If you have few and lots of sliders, yeah, you're kind of shooting, you're throwing darts a little bit. I don't know what to say because it's such an unexplored area of research. I can say this, the minimized Procrustes distance works pretty well no matter what, but it assumes spatial independence. So that's like assuming there's no phylogenetic signal in my data, so I don't need to do PGLS, right? It's dangerous. Yep. So first off, thank you. I was sort of curious, is the like matrix map you're doing is the minimal like processing? Would that be a place to go for computing the stuff on the graphics card? The sparse matrix algebra? Yeah, or even not really. I think so. Yeah, so systems that have their own cards for graphics can you do something like this, like remove pixel information that's not inherent or something, so that videos are faster? I'm not
in the crypto community or whatever, they do a lot of like highly, extremely parallel
Right.
processing.
Yeah, I don't see why it couldn't be used, but it's that's out of my wheelhouse, to be honest. Like, you got a question?
Yeah, amazing talk and very, very exciting. I wanted to check my understanding of what you're talking about integrated analysis of multiple parts. Are you talking about like analysis where you have landmarks on the skull and the humorous or something different?
Yeah, so for example, in that paper, we used larval salamanders, tadpoles, right, that are developing into salamanders that have head morphologies that might be really important. You know, what do they eat? What are they predatory or are they herbivorous? And tails, which are functional for swimming. And well, the way you swim probably is associated with the way you eat. And you know, studying fish, we know this to be true. But there's a lot of body in between, a lot of flexible body in between that tail and that head. So you can't really like fix those things in one landmark configuration, but you can get landmarks from both and you can combine them as an integrated phenotype.
And so what did you mean about weighting?
Okay, so yeah, we could weight them based on their original size. All right, so let's say the tail happens to be twice as large as the head. Then we might use a weight of 0.67 for the landmark configurations for the tails and 0.33 for the head when we combine them to make sure that the head stays in relative proportion to the tail. But that need not be the case because you could say, I think head morphology is more important. I'm going to kick it up a little bit. So when you combine them, you don't just combine landmark configurations that are equal size, because what you're doing is inflating the importance of one structure compared to the other. You have to have some prior notion of the relative size of these things or the relative importance if you want to fudge it in a particular direction. Well, we wrote this paper with Krusty's residuals, so yes, they will affect, you end up with unit size structures. So if you had 30 landmarks here and it's twice as big and 60 landmarks here, and now you want to deflate this and inflate that when you combine them, it could have some implications, and I don't know what they are fully.
You want to have standardized number of
It's a good question. I think you know, this pervades a lot of other areas. On Jolly's case, where she's doing lots of modules, right? If you have one module that has lots of landmarks and one that has little, you're going to get different interpretations than if you have maintained the density. And I know you spend a lot of time thinking about these things. So yes, there's an implication. What the implication is, I can't say until more research has been done.